So my name is Justin Searle. I'm a managing partner for a company called Utilisec. And we specialize in doing security consulting, especially penetration testing and control systems. So we end up doing a lot of work with different types of governments, helping write guidance documents for critical infrastructure, electric, utilities, oil, water, gas. We do penetration testing for those same organizations and companies. I'd say about a third of what we do penetration testing-wise is probably for what we call asset owners. So electric utilities, oil, gas, manufacturing, automotive manufacturing, transportation organizations, anybody that has some type of a control system. That's about a third of our work. About a third of our work is with different government entities and government projects. And then a third of our work are with vendors like General Electric and ABB and Siemens and Rockwell, organizations that go through and actually create and manufacture this type of equipment. So what we're here today is we're going to be talking about one of SCADA's easiest and one of the most basic protocols, which is Modbus. And the reason why we're talking about Modbus, it's a very old protocol. It's been around for ages. But the nice thing about Modbus is out of all the SCADA protocols, there's almost no SCADA protocol that is as widely used as Modbus. There's more devices that support Modbus than almost any other protocol that's out there. So it makes it very nice to use. It's also a very simple program too, a very simple protocol that we can get into and understand. So what we're going to be doing, so as I'm talking, I have a couple slides to cover some background about what SCADA is, a little bit more about helping understand exactly where this fits inside of our world. And while we're doing this, please, if you want to follow along with the exercises, grab the DVD, grab the USB key, and start installing the software and get it up and running. So in about 15 minutes, when we start doing the hands-on exercises, you'll be able to have that data. So that'll be great. Like I said, you don't have to do all of it. If you want to do just portions of the exercise, one of the first things we're going to be doing is we're going to be working with a PCAP file that's a capture from a control network that has different types of control protocols. We're going to go in and we're going to extract out some of the Modbus and analyze some of the Modbus traffic there. If you want to just do that, I do have just the file itself on the USB key if you want to work with that. Let me see how my other USB keys are going. Oh, not quite done yet. Does anybody need USB instead of the DVD? If you need it, come grab it. So we have two USB keys up here. Feel free to grab one and just bring it back up when you're ready. Okay, so the virtual machine we're going to use today, if you choose to use the virtual machine is called Samurai STFU, or the Security Testing Framework for Utilities. This is a distribution that I put together about a year and a half ago and have been updating. We've had, I'm about ready to release the 8th update, so I'm updating about every 3 to 4 months for the distribution. But it's a distribution that I created really to try to give anybody that wants to do some type of a security assessment or penetration testing inside of control systems, some distribution that not only has tools available, so if you're familiar with Backtrack or Kali, that has a lot of pen test and attack tools pre-installed and pre-configured, very similar. We have those as well, but we've really tried to go beyond that. On what we're trying to do. It's not just a set of tools for us. It's really more of a testing environment for us. So on this distribution, the Samurai STFU distributions, you can access that just up at the website I have up there, downloading the newest versions and other resources we have available up there. If you're really interested, we do offer various types of training. The last 2 days here at Black Hat, I've been doing a two-day class on assessing and exploiting control systems. At Las Vegas, Black Hat, we do a 4-day version of it. And for the SANS Institute, around different locations around the world, we'll usually do a 5-day version of that course. And I also offer that course as an online one, too. So what we're doing today is going to be a small excerpt, kind of a little peek into what we do inside of this course. But on this virtual machine, the virtual machine, we really create it primarily for the multiple different asset owners and vendors that are out there that are creating control systems and trying to manage and run control systems. We end up having these control systems that make up what we call our critical infrastructure. It's the oil and the gas and the power that all of us are dependent upon for our daily lives. And so really we wanted to try to give the community something they can go through to do to be able to test these equipments and try to find the vulnerabilities and get rid of these vulnerabilities before attackers can get into them. So that's always been my primary audience. My secondary audience for this distribution that we're using today is really set to security contractors. Okay? Anybody that's in the security field that wants to learn more about these systems, this distribution is created just to give you the tools to do it, but also to give you some experience to it. We have lots of different capabilities. We have documentation on not just the tools, but documentation on architectures and what different architectures look like in control systems. You know, documentation describing what's the difference between a SCADA system, what's the difference between a PCS system, what's the difference between a DCS system. Okay, all different types of systems out there. We have documentation in the distribution for methodology. How do we go through and do penetration testing? There's a document in the distribution that I created for one of the government-funded projects that's called the Guide to Penetration Testing, and it breaks penetration testing for control networks into 56 different discrete tasks to try to give us more visibility into how to perform this work. We have documentation on protocols where available. We have not just documentation on protocols, but I have simulators for as many protocols as I can get. It's pretty thin. I only have 3 or 4 different protocols right now for simulations. But I also have packet captures. The next release, which I'll be uploading here in the next few days, is going to be 1.8. That release will have probably upwards of 10 to 12 different control system protocols capture files. So you can go through and understand what these control systems look like, understand what these protocols look like, and get some experience working with these protocols. And then I also have different things like dumps from memory and different EEPROMs and flash chips. Because part of what we do in our penetration testing is we don't just work with the network protocols like we're doing today, but we also go down and we work with the embedded hardware and the embedded electronics, the firmware and the microcontrollers and the flash that store all the security keys and all the security and the defenses in these devices. Which is another attack angle that we do in the class to try to exploit them. Okay, so that's what we're really trying to do with these security contractors, give them these tools. And then also the third goal, or the third audience I have for this distribution really are the universities. I've been working a lot with university professors around the world, trying to help the different universities start getting more knowledge and more capabilities into their programs, to be able to start teaching people at a younger age and get them interested in not just IT security, but really control system security. Because we have such a need right now for people doing work in this area that we really need to bring up more people. And so this distribution, like I said, like Kali, it has lots of pen testing tools on it. They're pre-configured, but we don't try to have all the tools on there. We try to just do the best tools. Okay, the cream of the crop. What are some of the best web pen testing tools? What are some of the best network pen testing tools? What are some of the best hardware pen testing tools? Which, by the way, Kali doesn't really have a lot of hardware pen testing tools on there yet. So we've been trying to be a home for some of those. Okay, so that's what this distribution is. When you get into the distribution, this is what the distribution will look like. Okay, so once you get it up and running, you have version 1.7 is what everybody will be using inside of this workshop today. Okay, but pretty basic, pretty straightforward desktop that we have here. If you want to figure out where all the tools are, just go down and click on the main menu. Inside the main menu under Applications, you'll see that there's a Samurai STFU menu item. If you click on that, it breaks all the tools down into what our methodology is. So I mentioned that document that describes our methodology. So all the tools are organized in the main menu based on methodology. So what are you trying to work in? So go to the main menu. Am I working with embedded electronics? Am I working with field technician interfaces? RF communications? Yes, we have a lot of RF, like software-defined radio and RF CAT tools built into the distribution. We have network protocols and then other types of user interface testing that we do. So if you wanted to go through and see, okay, well, what do we have in the way of embedded electronics? You can see that, well, now we have a different section. When I'm working on embedded electronics, am I working on data sheets? Am I working on data dumps, bus snooping, string analysis, entropy analysis, key analysis? So what exactly are we working on on that portion of the distribution? And you can keep on digging down until you find all the tools that are available. Besides the tools that are available, we do have several different files. Probably the two most interesting to you are going to be the samples file on the desktop. We're going to be doing some exercises from here today. Inside of the samples files, if you go into the network capture protocols, you end up finding all the different PCAPs and captures of some of the different ICS protocols that we have. So you can kind of see the ones we have. We're going to be working with the Modbus one. today is the capture that's inside of there. We also have on that desktop our reading room, which also is something that's very interesting. A lot of the documentation on methodologies and architectures and security defenses are found here inside of the reading room. So I mentioned the guide to penetration testing. That's right here, the NESCOR guide to penetration testing. So it's focused on electric utilities, but it's really a methodology that can be used for any type of control system. I'm working on a new updated version that will remove the electric utility specific portions of it. So it's a more generic. But then other types of documentation and guidance documents from various different organizations around the world, both nuclear, the energy sector, and other organizations. Okay, so that's the distribution. Once again, if you just came in, there is a DVD up here that you can go ahead and grab, and you can download this distribution. It's just a virtual machine that you can get up and running. Feel free to come grab one if you want one. So there's the DVD. If you do not have a DVD drive, I do have some USB sticks that are available that you can go ahead and copy. If you use a USB stick, please just bring that USB stick back up after you're done so somebody else can use it. I only have a couple of them. Let me check to see if my other ones are done. Okay, and it looks like they are done. Okay, so here's 2 more USB sticks. Oops, and there goes my video. Okay, so who needs USB? So I have, so please just copy the USB information off. If you do not have a DVD drive, I only have 4 USB sticks going around. Yeah, so please pass those around. When you're done with them, bring them back up here so everybody else can get to them. If you do not have a computer with you today, feel free to download the distribution anytime you want. It's a free open source distribution. Grab it anytime you want. Like I said, I'll have the newest release posted up here probably within the next 5 to 6 days. Okay. So, as you're working on this is the general instructions to get that virtual machine up. So if you've ever worked with virtual machines, it's really straightforward. So on the USB or on the DVD, you will find the Samurai STFU virtual machine. Okay, you'll just want to copy that to your hard drive. Once it's to your hard drive, unzip it. And then inside of VMware, just do file open. You don't import it. You have to do a file open. And and then point it to the VMX file, which is the configuration file. If you are using VirtualBox, okay, you probably are familiar with using VirtualBox, how to get VMware images in. Just inside of VirtualBox, create a brand new empty virtual machine without a hard drive, and then you go tell it that you want to use the VMXK files inside of this folder, which is the virtual hard drives. And that will get VirtualBox up and running with the distribution. So keep on working on that. In a little bit, if you're having problems getting it running, I'll go around and try to answer questions for anybody that has any issues going on with that distribution or trying to get it up and running. Okay, so let's go ahead and talk just a little bit about control systems, to give you a little bit of background. How many people here already have a fairly decent knowledge of control systems or some form of experience in control systems? Awesome. Good. Okay, so most of you guys are new. Let's go ahead and give you guys some background. So when we talk about a control system, the first thing that we always hear inside of these security conferences like Black Hat and DEF CON is they always talk about SCADA. Okay? One thing we need to understand about SCADA, when we talk about control systems or industrial control systems, okay, ICS, industrial control systems, okay, control systems in general are about this big. Okay, we end up having a very broad space of what industrial control systems. If we talk about outside of industrial control systems like Internet of Things, it's even bigger. Okay, Internet of Things is a type of a control system. A subset of that is industrial control system. Industrial control systems are going to be things like electric utilities, water, gas, transportation like the street lights that we have, other types of manufacturing, be it automotive manufacturing or product manufacturing or chemical manufacturing. All of that is considered industrial control systems. Now, inside of industrial control systems, there's a very, very small segment of that is called SCADA. Okay, so when we talk about SCADA inside of IT security, we often think SCADA is control systems. It's not. SCADA is actually a very small portion of it. What a SCADA system is SCADA is a type of control system that is geographically spread across a large distance. So what makes up SCADA? The energy sector, the electric utilities, oil and gas, they make up a very large part of SCADA. Because when they have their pipelines, when they have the remote oil refineries, when they have their different types of generation plants that generate electricity, okay, inside those plants is not generally considered SCADA. However, to get the electricity from those generation plants to the homes and the businesses, or to get the gas from the drilling stations to the different locations where we can actually use it, we end up having to control and monitor all of that network over a large geographic region. So this is what we call SCADA. So you'll have a pipeline, and on that pipeline, taking oil and gas from where it was pulled out of the ground to where it's actually being processed, you're going to have multiple different valves and sensors along that line to be able to measure what the pressure is and be able to control where that flows and the rate at which it flows. Okay, so that's a type of a SCADA system. Inside of the IT security, we've kind of gotten a bad habit of talking about SCADA as the world of control system, because when we talk about attacks, that's some of the first attacks that come to mind. Okay? But when you talk about different types of control systems inside of a generation plant or a drilling station or a drilling platform, okay, or a manufacturing warehouse, okay, that's generally not considered SCADA. If we want to have a term that describes a lot of those systems, we generally call them DCS, or distributed control systems. Okay, so different types of needs. They usually are working with pulling information back from the sensors every 1 millisecond to 10 milliseconds on some of the faster systems, where SCADA is usually working in the resolution of about one type, or pulling information back from the large network maybe once every 2 seconds or once every 10 seconds. So there's a very, very big difference between how we're actually working with these. Now, when we talk about these control systems, like SCADA, okay, so since SCADA talks about a large geographic region, SCADA always will go through some type of a WAN connection, a wide area network connection. Now, when we have this wide area network connection inside of our SCADA systems, okay, so here's my WAN. Inside of that WAN, we're going to use lots of technology. It could be satellite, like VSAT connections. It could be cellular. It could be some type of proprietary microwave communications or other type of an RF communications. It could be dial-up. We still use a lot of dial-up inside of our SCADA networks. But that WAN becomes kind of the central point. Now, on the control center side of the WAN, so back up where we have the control centers and the master servers, we'll have some type of a master server, and depending on the SCADA system that you're working on, it may have very different types of names. Okay, you may hear it called a front-end processor. You may hear it called an MTU, a master terminal unit. You may hear it called a head end. Okay, the names are countless. What we could actually call it. In general, we'll generally call them today just a master server. Something that is pulling information from the various different control processes in the field, trying to understand what's going on with them. Okay, now to that master server, while it's trying to coordinate all this, it has two other types of devices that are often connected to it. We'll generally have a historian, okay, and that historian is a form of a data store. Often it's going to be a database. It may be a relational database, like an Oracle database, okay, or a Microsoft SQL Server. That's something that we definitely could have. But when we talk about historians, we're not implying a relational database. It could literally be a file server that's sitting there. It could be an FTP server that's sitting there. It could be a big data server, like an Elasticsearch database or a NoSQL database. Okay, so a historian just means that we have something sitting there that's storing information about the processes. And they generally store what we call time series data. So information that we pulled from the processes, knowing, understanding of what changes we've made and what our sensors read from the processes. The other thing we have connected to the master server is a human-machine interface. And a human-machine interface is going to be an interface that basically has a nice, pretty picture describing what the process looks like. So if it's an oil line, you may see a picture of an oil line with pictures of valves in the oil line and different notes of what part of the region that oil line is, or that valve is. And they may have little buttons that allow the operator to shut the valve or to close a valve or toggle what type of flow is going through that valve. Okay, so that's an HMI, or a human-machine interface. So it's a form of an interface that allows our operators, the ones that make sure the process is working properly, to control and monitor that. Okay, now there's another type of interface besides a human-machine interface. There's usually some type of an administrative interface as well on the head end that allows us to configure protocols and all the technical information. Okay, more like a normal admin interface. Okay, but we'll have both of those. As for what they're actually each running, when we're doing pen testing, since we're at Black Hat, we talk about attacking things, right? Finding vulnerabilities in things. Our head ends and our historians, most of them are running either Windows or Linux now. Older ones may be running a form of Unix. Really old ones might be running something like a mainframe software, or yes, even maybe DOS. Okay, Windows XP, yeah, you know, because we call Windows XP a server. So it happens. Okay, HMIs, most modern ones are web-based now. So if you do web pen testing, you have some experience there. Then we get down into the field. This is the more interesting thing that we're getting into, that we want to go to for Modbus. Okay, down in the field, we end up having things called PLCs, IEDs, and RTUs. Okay, now a PLC, a programmable logic controller. So this is an example of a PLC. This is one of the world's smallest PLCs. I absolutely love it because it fits inside of my pocket. This does speak Modbus. You can buy one of these for $49 US. Okay, great company. One of my favorite ones. All the software to be able to program it, all the software to be able to build an HMI for it, all 100% free, written in .NET, modern software, very beautiful software. Beauty is not a term you usually describe most PLCs and PLC software. It's usually very old and very archaic and very ugly. Okay, this is actually a great little product. So if you want to be able to play around with one, I'll put the URL up in just a minute of where you can buy one of these if you're interested. Okay, but PLC's programmable logic controller. What its purpose is it connects to different types of sensors and actuators. And on those sensors, we call them monitor points. So we may have a sensor that's telling us what the pressure is in the pipeline. And we may have an actuator, which is going to be the valve, to turn the valve on or off. Actuator is just a generic term, meaning we're going to change something in the real physical world. Okay, so these control points and monitor points on the sensors and actuators allow us to control whatever process we have. And that PLC has a program built into it that will automatically regulate and try to control that process. So an engineer will create a program that says, okay, this gas line has to be able to flow at this rate, and these are the safe boundaries for where we can actually have volume and pressure. And that PLC will have that program built into it to make sure that it stays within those operational boundaries. It's very similar to like a thermostat in our house. Okay, a thermostat in our house, we say we want it to be 22 degrees, and it will turn on the fans and the AC and the heater to make sure that we stay right at that 22 or close to that 22 degrees. Okay, so that's really what a PLC is doing for us. And a PLC could have something very small like that that has 6 inputs or 6 outputs. Or if you get into some of the PLCs inside of the generation plants, it could be thousands of inputs and outputs that it's sitting there controlling. And a program that's multiple layers deep with subroutines going through and trying to control what's going on inside of that facility. Okay? Then we get down into IEDs, the intelligent endpoint devices, and the RTUs. Okay, so PLC is that main program logic controller. An RTU, often in a SCADA environment, is put in front of a PLC because an RTU acts kind of like a gateway type device. It can do translations from one SCADA protocol to another SCADA protocol. Okay, often going from a more advanced protocol on the WAN side to something that's more basic protocol like Modbus on the field side. Okay, and so that RTU could connect to multiple different PLC devices, or we could go ahead and talk straight to an IED. An IED is an intelligent endpoint device. It just means that it's kind of a black box that we talk directly to, and it handles all of its I/O all by itself. Kind of an intelligent thing that we don't have to do anything. PLCs, we're often having engineers wire them up and build the networks and engineering everything. An IED is something that's self-contained, kind of like a smart meter. Okay? Smart meter is a self-contained little black box. We talk directly to the smart meter and get its information from it. It doesn't have to go through a PLC. Okay, so those are our basic architectures that we have available for us. To go ahead and give you one example of what this looks like. Let's go ahead and talk, I've given you examples of oil and gas. Let's talk about an example for an electric utility. So say here in Singapore, we end up having an electric utility that has multiple different substations around the country. And these electric utilities are going to have these substations as well as their control centers, as well as all their customers, the resident customers and the commercial customers, that they have to try to manage all of this flow of electricity. What this diagram represents, and I lovingly call this the spaghetti diagram, and no, you're not supposed to be able to read everything on this. You'll have to be able to get the slides later, and you can see it a little bit better there. But on this diagram, this tries to show the major systems found in most electric utilities and the communication links between each of those major systems. Now, when we talk about SCADA, SCADA is only a part of what an electric utility has to deal with in their control networks. Okay? We end up having what we call the distribution SCADA. So here's my distribution SCADA server, and it goes out and talks to the substations, which are those fenced-off areas that you'll actually see around different cities and residents, where all the power lines come into, and they have some control houses inside of there, and they distribute the electricity out to the homes and the businesses and the apartment buildings. Okay? So that's our master. That it goes out, it talks to the field, to all these different types of devices. We have the same things on transmission. So when you have large countries that's sending power over large distances, we call those transmission lines. So they usually have a different type of a SCADA system to control that power over a long distance. And then we have different types of SCADA systems that are talking to the power plants and pulling information from the power plants and trying to initiate the flow of data there. Now, if I look inside of one of these substations, so right here, if I take this little section and I zoom into it, okay, this is what we're often going to find inside of one of those substations. Okay, so inside of the substations, we have WAN connectivity going into some type of a router quite oftenly. Sometimes we have modems, or dial-up modems coming back in. Okay, sometimes multiple different modems coming in. Inside of the substation, we'll usually have some type of a major gateway or a device that tries to coordinate all the different systems inside of the gateway. And then inside of the substation, we're going to go ahead and have different types of communication processors, different types of RTUs, those remote terminal units. We may have different types of relays, different types of PLCs that are doing communications, or other types of IEDs, like a digital fault recorder or a meter. Okay, so lots of different protocols and lots of different types of technologies found at this area. Now, what we're interested in is the Modbus protocol. And where do we find Modbus? Well, you can find Modbus in most sections here. You never know where you're going to find Modbus. It just kind of pops up everywhere anytime you're working with control systems. But quite often, PLCs end up doing a lot of Modbus communications. Our RTUs end up doing a lot of Modbus communications. And then sometimes on these communication processors or the relays, you'll end up seeing some Modbus communications as well. Okay, so looking at a PLC. Here's that PLC I told you about. If you're interested in buying one of these PLCs, fairly inexpensive, Velocio.net is where you can go and grab this. It's about $49 US is their basic model. It is by far my favorite PLC on the market today. It's small, it's teeny, it works very, very well. It's a fun little project hobbyist one, and we can start going through and doing some research on it as well. Other PLCs, my second favorite PLC is a Siemens S7-1200. They run about $300 to $400 US for those, and that's generally without the software. You end up charging the extra for software as well for that. But great little product. So if you're interested, go pick one up. They're actually fairly cheap and inexpensive. Great for being able to do your own research. The other nice thing about them is it speaks Modbus over the USB cable. All your other PLCs, you'll have to buy a special cable to speak Modbus to it via a serial interface. This allows you to speak it right on the USB port that you're already communicating with it. So it works very nice that way. Okay? But on my PLCs, no matter what PLC, something very small like a $40 PLC, or you go to a $100,000 PLC that's being put inside of some of the plants, okay? All of our PLCs are going to have some type of a communications port to go upstream to the master server or whatever other software is managing it. They're going to have some type of an input and some type of an output. Now this one we have some analog inputs, more analog inputs. We have some digital outputs, and we have some digital outputs here. Okay, so these are all how we're talking to the outside world. So all the outputs, so output, output, I guess only these two are outputs. So the outputs are going to send the control signals out to make changes into the environment or whatever process we're doing, maybe close a valve. The inputs are going to be the sensors that we're monitoring to try to figure out what we need to do with that process. Okay? When we are going through and using a protocol like Modbus, Modbus is a simple protocol that allows us to say, read this input or change this output. And that's all Modbus does. Very, very simple product. Very, very simple protocol. Modbus has to be communicated from the master down to that PLC unit. Okay? And it just says change or read or write is really all that we're really doing with Modbus. Now, there's other protocols besides Modbus. If you want a kind of a list of some of the major protocols that we have in control networks, here's kind of a fairly succinct list of the most major or the most popular protocols you'll come across inside of our system. So notice that Modbus and OPC are two very common ones. They work at different levels. Modbus is down on the PLC level. OPC is a protocol that we often speak up at the HMIs and the master servers, kind of higher up the communication architecture. So those are some we have in our manufacturing. These are mostly these lower level protocols that might be used instead of Modbus. Inside of the energy sector, like oil, gas, and electric utilities, these are some of the protocols that they may use instead of Modbus. So depending on where you are and what types of systems that we're working with and the specific needs that you have. Okay, so you guys ready to talk about Modbus? What we're here for. So Modbus is a protocol, a control system protocol, very simple one. It was made back in 1979, so it's a very old protocol, very simple protocol. It is widely implemented to the point where it has hundreds of vendors that are producing it for their products. Okay, like I said, probably one of the most produced and most implemented protocols that's out there. It was a protocol that was made to talk between a master station, or some type of a, not master station, excuse me, some type of a master server, going out to some type of a field device, like an RTU, a PLC, or an IED out inside of the field. When you're doing it, some of the general rules of the protocol, the master station is the only one that can talk. He's the only one that can initiate conversations. So what we call is we have the master that is pulling the different field devices. He will pull it to try to be able to do read values. And often these will be very, very discrete, synchronized read values. Inside of SCADA, like I mentioned, a lot of electric utilities will do reads of their substations every 2 seconds. So we're constantly going through, and the master will say, okay, what's the current status now? What's the status? What's the status on all the sensors? And it pulls that back into the master. The slave is only allowed to talk. So when they call it master-slave, slave is that field device. So that field device is only allowed to reply. Modbus has no capabilities to allow that slave device or that field device to be able to speak on its own to send information back up. The newer protocols that we had on the other screen, most of those, you can go to the field device and say, okay, at this time period or when this event happens, go ahead and automatically send information back up. Modbus cannot do that. Modbus is a very, very simple protocol. So field devices cannot initiate conversations. It makes it very easy to analyze. Also, it's a very simple request-response protocol. Literally, I say read this value, and it gives me that value. I say write this value, it gives me that value. And that is the extent of Modbus functionality. So very, very simple protocol. Okay, it was an open protocol in the 2000s. It was proprietary before that. Now it's very, very popular now. There is no security whatsoever anywhere in Modbus. There's no encryption. There's no authentication. So you could have a master server going out and talking to 1,000 different field devices. And if you can get on that network, you can go ahead and use any of the tools that we'll be playing with today and go ahead and say, okay, I want to go ahead and send a control signal out to this field device and change some value in there. And that field device will automatically do it for you. Okay? No security whatsoever built into the protocol. If we have organizations like asset owners that want to be able to protect their Modbus communications, they literally have to go out and put firewall devices out in front of their field devices and build some type of a VPN tunnel, some type of authentication gateway, or some type of a firewall rule set limiting who can actually send those signals and who cannot send those signals. It's the only thing we can really do. Modbus doesn't have that feature. Now, when we look at Modbus protocol, this is what the Modbus protocol looks like. Okay? So we have some type of a transaction ID. That's the very first part of it. That transaction ID allows us to be able to say, okay, here's the request from the master. The slave or that field device will reply, and it has to reply with that same transaction ID. It's the way that the master server knows that this request I sent out, this is the response that pairs with it. Okay, so that transaction ID has to be the same on a request and response, so it pairs that information together. Protocol ID, all zeros, always all zeros. When we talk about TCP/IP version of Modbus, there's 2 serial versions. We're talking about the TCP version. The TCP version of Modbus, there's only one, and it's version 0, and so you should never see anything but zeros in that section. Okay? The length. The length is going to be an identifier saying how much data comes from this point on inside of the packet. Then we have a unit ID, so actually 6 bytes. So I have 1, 2, 3, 4, 5, 6. So yes, that is correct. Unit ID talks about which Modbus device it is. Remember how I said you can talk to a RTU, and that RTU can talk to multiple different types of PLCs out in the field? Well, if you talk to an RTU with Modbus, you can actually say, I want to talk to Unit ID 1 or Unit ID 2 or Unit ID 3. So Modbus has a capability built into it to multiplex to multiple different types of devices beyond a single gateway device. Okay, so Unit ID 1, if you're talking directly just to a PLC, it most of the time is Unit ID 1 is what they usually have it programmed to. Function. The function is going to be the command that we're actually doing. So this function is going to be a read. And then we have the function's data. What are we actually trying to do? Here specifically, we're saying we want to read address or register value 8D2. So that's going to be the address that we want to read. And we want to go ahead and read 2 words of data out of there, or 4 bytes of data. That's how we decode that protocol. Okay, so simple protocol. That's the extent of it. That's what our packets will always look like inside of Modbus. If you want more information, Modbus does have the full docs on it. It is an open protocol, so you can go ahead and you can download the full standard for free and dig into exactly how it works. Okay? What I want to do is go ahead and show you just a little bit more for the command. So here's the function. There are several different functions we can use, and so here's a list of the major functions that's out there. When we talk to different types of PLCs, okay, I showed you on these PLCs, we have digital inputs and outputs, and we have analog inputs and outputs. If we want to talk to a digital input or output, we call these coils in Modbus terminology. Okay? So if I want to go ahead and talk to digital, which means bit level access, either on or off, we can go ahead and we can read coils or we can write to coils. Okay? When we read coils, we can read discrete inputs or we can read coils. Discrete inputs basically are the input lines, the digital lines coming into this device. My read coils are going to be my outputs. I can read the current state of what my output is on the PLC. Or I can go ahead and write to that coil and change what that output value is on that PLC. So be able to turn some type of a switch on or off, turn a valve on or off. Okay, so that's all our digital. So this is digital in and out. All of it is bit level access, 1s and 0s that we're sending. Now if you want to talk to an analog input or an analog output, okay, analog is what we call registers. Analogs, by default, will be 2-byte values, okay, or a word is what we usually call it. Okay, and when we talk to those analogs, it's 16-bit access, or 2 bytes, and we can go ahead and we can read the input. So if we have an analog input, we can read that current value on that input, or we can go ahead and read the holding registers, which is my output. So what's the current state of the holding register? Okay. We can go ahead and we can write to that holding register. So basically change what my analog output is. So if I have an analog output, basically say it's going to be something like setting a temperature for a thermostat or setting a temperature for some type of a vat that we're boiling. We can go ahead and we can set a temperature, and the PLC will automatically know based on whatever temperature we set. So we set it to 150 degrees Celsius. Okay, the program inside of here will know that 150 degrees Celsius is equal to this 16-bit number to be able to send it on to whatever product that we're doing that's working on it. Okay, so a bit level access, byte level access for the analog. And then we have one feature that's not very often implemented. Most Modbus devices don't have this implemented, but sometimes you'll have a Modbus device that allows you to either write or read files from the Modbus. I've seen once or twice where they've had log files where you could actually pull a log file off of it by doing a read. I've seen at least once where they had a firmware where you could actually write a firmware and flash the device via Modbus by writing the file to it using that command. So as a side note, I actually spoke to the engineer that designed this last night for the first time, and he said that in their newest product, he's actually considering adding that field record access to be able to read different types of memory locations or data sets, storage locations on this device. So kind of fun. That'll be coming. Okay, and then we do have some special commands that are outside of just the simple read and write. These often are not implemented. If they are implemented, they're usually implemented a little bit more proprietary. There's multiple different types of diagnostic information that may or may not be implemented. and then some type of an encapsulated transport if you want to try to tunnel something over Modbus. I've never seen that implemented myself. Okay, so here's a summary that we have for the reads and the writes. These are the most common things. If you ever look at Modbus captures, which we're going to be doing in the next slide, the first hands-on exercise, is if you're ever looking at Modbus captures, almost every single command you'll ever see sent on the network will be one of these 8 commands. Okay, it's very rare to see something outside of one of these 8 commands in normal control system traffic. Okay, so when we have reads, we can either read a coil, or we can read the discrete input on the device. We can read holding registers, or we can read input registers on this device. So a couple different things that we can go through and read on these devices. Okay, we can also go through and we can write to coils. Okay, we can go ahead and we can write to a single register value. We can write to multiple coils or write to multiple registers. So once again, writing to a coil means that we're changing the output of a binary. We're changing a binary output, turning something on or off. If we're writing a single register, we are sending a control signal to go ahead and change some type of an analog output. Or we can go ahead and change multiple binaries or multiple analog outputs on this device. Okay, so that's how our protocol works. Now, what we're going to do, we're going to go ahead, I have an exercise for you. So the first hands-on exercise is on the USB or on the DVD inside of the virtual machine. Okay, inside of the virtual machine, you will find a PCAP file. Okay, that PCAP file is a Modbus capture. So if you have the virtual machine running, okay, inside of the samples files, you'll go down to our network capture protocols, and you'll go into your Modbus SCADA. And inside of here, you will see a PCAP file. So here's the Modbus TCP PCAP. What I want you to do is I want you to open that up inside of Wireshark, and I want you to try to answer some questions. If you have the USB stick instead, okay, on the USB stick, I didn't get the capture actually on, I don't think I got the capture on the, did I do that? Oh, it might actually be on the DVD. Inside of the DVD, if you look inside of the DVD, I know it's on the USB stick. The USB stick actually has a smaller set of files on it, so it was easier for you guys to copy across. Let's do a few course. Give me 1 second. Yeah, I think it's actually there. I think on the DVD, if you look inside the DVD, you should be able to look inside of there under the lab files, network protocol capture, SCADA Modbus. You should be able to go through and find the Modbus TCP file. So go ahead and open that up inside of Wireshark. And the questions I want you to try to answer, and I'll walk around and help people, and then I'll do it up in front of the screen for everybody after you guys have a chance to play with it. So I want you to answer these questions. Or if you're online, you can grab the capture from cloudchalk.org too. It's up there. So what IP address is the master on? So I want you to go through and analyze that traffic and identify where the master is, identify his IP address. Then I want you to go ahead and try to identify how many slaves is the master talking to. So by looking at the Modbus traffic, I want you to go through and try to see who that master is talking to and be able to identify and give me a count for how many different PLCs is that master speaking to. Okay, then the next one is the master writing any data to any of the slaves? So go through and look at the data sets and try to identify if the master is sending any write commands. So a command that's a 5 or a 6 or a 15 or a 16. Okay, those are going to be the write commands. So try to identify if he has any write commands going on. Then the final one is, does the traffic spike in the middle relate to Modbus? So in the capture, there's a spike right in the middle of it. If you look at a summary under the statistics IO graph, it'll show you a summary of all the data. You'll see a spike right in the very middle. I want you to try to figure out, is that spike having to do something with Modbus, or does it have something to do with some other protocol? Okay? So go ahead and take the next 5 minutes to try to answer some of these questions. I'm going to go ahead and walk around, answer any questions, or if anybody has problems getting the virtual machine running, I'll be able to take a few minutes to help you out there. Okay? All right, let me go ahead and walk you guys through some of this so that way we can get through it before we get to our break here. Okay, so here's my capture. The easiest thing to do if we want to modify, if we want to analyze Modbus, notice that we have a whole bunch of other traffic here besides Modbus. If we want to analyze Modbus, the easiest thing to do is go ahead and find a Modbus packet. So here's a Modbus packet. And then in the descriptor here, where it starts breaking it down, notice we have the Modbus section. If I go ahead and just right-click on that Modbus section, I can tell it to apply a filter selected. And what that's going to do is it will go ahead and only show me any other packet that has that Modbus section in it. Okay, so basically all the Modbus traffic. So now everything in my list is filtered for only Modbus. Okay, so I've zoomed in and I'm only looking at the Modbus traffic now. Okay, now to go through and do analysis of it, one of the easiest things to do inside of Wireshark to analyze large data sets is to go ahead and look at the statistic views. So if I go into statistics and tell it I want to look at my conversations, okay, that's going to go ahead and show me every single Modbus conversation. And I can look at that conversation at the Ethernet level, the IP level, or the TCP level. Okay, so on the, let's go ahead, we'll leave the TCP level. Okay, on that TCP level, notice that it's showing me a whole bunch of other protocols besides Modbus. It's because by default it doesn't actually follow my filter. So if I go ahead and click right here, limit to display filter, this will actually limit the statistics view to be the same exact filters I have in the other window to only show me Modbus traffic. Okay, so here is all my Modbus traffic. And I can see that all my Modbus traffic is coming from the IP address .10 going to a whole bunch of different IP addresses inside of this address B column. So we have one single Modbus master, which is .10, talking to a whole bunch of slaves. And they're all doing it across ASA Apple protocol, which is kind of funny. It's because that's the actual protocol registered to port 502, which is what Modbus uses. Modbus does not have a registered port, but it always uses 502, is by default. So if you turn off the name resolution, you can just see that it's port 502. Okay? Now, to find out how many slaves, you can count by hand, or if you just come down to the IP section, which will summarize all conversations by IP addresses, notice all 10 is starting, all of the ones coming back, there's 13 of them. So 13 different IP addresses that .10 is communicating with. Okay, so I have one master, I have 13 field devices or slave devices that I'm communicating with. Okay, so that's the first two questions. What's the master, and who are the slaves on that conversation? Okay, now the next question was, of that, is the master writing any data to the slaves? So if I come into the Modbus and I decode some of the communications, inside of the Modbus decode, you'll be able to find that function. Okay, here's a function 4, which is a read and input register. What you can do is you can go ahead, if you already know your functions, if you just right-click on that function and say, hey, I want to go ahead and I want to apply a filter as selected. What that's going to do is it will only show you Modbus packets that has a function of 4. Okay, so I'm going to select that, and this automatically builds the filter string for you. So if you don't know the query language, automatically builds the query for you. Okay, so this shows me all the queries that's using command 4, but I don't really care about command 4. I'm caring about the write commands. That was the question. Is the Modbus master writing anything to those field devices? Is he changing them or sending control signals? And if I look at my little cheat sheet here for the protocols, that's going to be function 5, function 6, function 15, and function 16. So all I do is come back into my Modbus. I change this to a 5, tell it to apply. There's no 5 messages, so we are not writing any single coils. Change this to a 6, tell it to apply. I'm not writing any register values either, so I'm not doing any single register values writes. If I go look at 15, which is writing multiple coils, I am writing multiple coils. So the master is sending control signals out to those field devices, but he's sending them using function code 15, not function code 5. And when he's working with the registers, filter on 16, and he is sending out multiple register writes. Not as many. Notice there's only a couple here. But so there's a couple times, at least to .44 and .46, where he is doing multiple function or multiple register writes to those. So he is sending control signals to those. So we were able to go through and see how do we do reads, how we do writes. We can identify what types of command signals that are being sent just by going through and knowing the appropriate filter that we can put. Now the last question I had was, if you look at the I/O graph in statistics, so statistics I/O graph, see that spike? We want to see if Modbus has anything to do with that spike. If I come down here to this little section, the y-axis, packets per tick, if I change that to bytes per tick, which means show me not how many packets that are being sent, but show me how big the packets are. Okay, notice that the spike's even more pronounced. It's a bigger spike when we look at it based on size. Okay, if I want to see if this has anything to do with Modbus, the easiest way to do it is come right down in here. We're going to add another graph item to graph, and we can go through and say MBTCP, which was the Modbus protocol name that we saw in the filter before. We're saying just show me in graph just Modbus traffic. Go ahead and tell it to graph number 2. And you can see right there, my Modbus traffic's flat. Okay, so Modbus was not one of the protocols that caused that spike. If you play around with this enough, you'll actually see that it's a Microsoft SQL Server using port 1433, which is actually doing a database sync, which causes that big giant spike right in the middle. Okay, but Modbus is not there. And this is important to note because if you ever go through and you're working with control system traffic is highly predictable. It almost always looks the same. You should see very, very consistency in almost all your control center protocols, which means if you're a defender and you're trying to build security defenses around a control system, you can usually go through and do anomaly detections on the network traffic to determine if you have some strange attacker or something inside of the infrastructure. Because an attacker's profile is going to look very different than your normal profile. And you can whitelist fairly easily most control system traffic if you have the right equipment to do so. Okay. So that is our traffic there for us. Okay? And that takes us to our first break. Does anybody have any questions before I release you to the morning coffee and we take a 30-minute break before we come back to start playing with sending traffic and talking to simulators? Can I pull up the PLC picture again? Yes. This one? No, that is not an RJ45. This does not have an Ethernet port. This one is just a USB port on it. So most PLCs, most PLCs on the lower lines do not have Ethernet ports. The least expensive PLC that you can buy with an Ethernet port usually runs right around $300, $400 US. So most of them have an RS-232 serial port on them. This one actually does it via the USB, or the USB port, which is nice because, like I said, all of us have USB ports. And so it's very easy to communicate via Modbus via that USB port. So that's one thing I really like about this PLC. And I mean, if you want to see it, you want to see the PLC? Oh, they're indestructible. They're built that way. Any other questions? Okay. Go ahead and go join your morning coffee. When we come back, we will start the session back up at 11:45. We'll go from 11:45 to 12:45, and we'll go ahead and we will build a Modbus simulator in class, and then we'll go ahead and we'll generate traffic to talk to that simulator. You will need to have the virtual machine running if you want to do this exercise, because the simulator is inside of there. If you have the USB stick, the simulator is a Java application, and the client we're using is a Perl application. So as long as you have Perl and Java installed, you might be able to do this inside of Windows or Mac. Yes, please. If you have the USB sticks, please bring them back up before you leave, so that way I can gather all the USB sticks for the next group if there's anybody else comes in that needs them. All right. So hopefully everybody enjoyed your break. We have another hour to go until we get to lunch. Okay, so what we did on the first half we went ahead and we went through and we looked at the Modbus protocol and we did some analysis of that traffic, of what Modbus traffic actually looked like. What we're going to do in this next segment is we're going to go through and we're going to set up a Modbus simulator. So that way we're going to create a simulator that acts like a voltage regulator. So take some type of an input voltage in and then so try to do some type of an input register and measure that incoming voltage and be able to regulate what that outcoming voltage is going to be. So that's what we're going to do for the second half of this section. Now, if you have if you weren't here for the first half, we do have the virtual machines that are available. If you go over on side of the DVD. Up here at the very front, you can go ahead and get a copy of the virtual machine and be able to use for this exercise. If you have the files from the USB. The USB key does have files that have the Modbus PAL Java machine that we're going to be using for the simulator, and it has the Perl script, MBT get, that we're going to be using for the client. So that's what we're going to be doing for the second half. Okay, so first off, what we're going to be doing, so this is Modbus PAL. Modbus PAL is a Modbus simulator. It's just a Java machine, so it works very, very easy. Little piece of Java software, a little jar file. What we're going to do is we're going to create this voltage regulator, and a voltage regulator is going to be our slave device number one. We're just creating one device, and this is going to have an input voltage that's a changing input voltage, and we're going to go ahead and we're going to regulate it down to a very, very fixed voltage, and then set some alarms of where those voltages can actually work within that range. To be able to simulate the input, we want to have some type of an input. So if we don't have a real input, we're going to simulate or use an automation for that input voltage to be able to try to create that fluctuation of what a real voltage would look like. And we're going to exaggerate it. We're going to make it so it's a very, very fluctuating input voltage so we can try to narrow that down and refine it. Okay, so first thing we need to do is we need to go ahead and start Modbus PAL. So I'm going to close down my Wireshark installation here. Okay, and then I'm going to click on the main menu. Inside of the main menu, I'm going to go ahead and do Modbus PAL. Okay, so there is Modbus PAL. So that's my Modbus simulator that I want to go ahead and use. Okay, and once my Modbus simulator is opened up, I want to go ahead and create my automation. So we're going to start right down here in the very bottom first. So what we want to do is we want to go ahead and we want to add an automation. And that automation we want to add, we're going to go ahead and give it a name, and we'll call it input voltage. So that way we have our input voltage. It's going to simulate what that input voltage is doing inside of our system. Now once I've created this automation, it's kind of an odd user interface for this tool. You click on the eyeball to be able to configure. Let's view the settings, I'm guessing. So if you click on that little eyeball, that allows us to open up a new window. Move it off the side so you can see it. Okay, that we can go through and create this automation capability. So inside of here, what we want to do is we want to go ahead and create a random generator. So click on random generator right here in the very bottom. Okay, when you create a random generator, it's going to ask you for a minimum value and a maximum value. So it's going to randomly choose values between that single range. Okay, so inside of this range, we're going to go ahead and say our minimum value is going to be 115. Our maximum value is going to be 125. Yes, forgive me, we're actually doing the US voltages, not the Asian voltages. So we're going to try to voltage regulate it to 100 and 120. So we're going to have our input that's fluctuating between 115 volts and 125 volts are what we're going to do. Okay, so once you've set this random generator, the last thing we need to do is we need to start it to make sure that it actually works the way we think it's going to work. So we added our random generator, we set our minimum and maximum values, then I'm going to go ahead and tell it to start playing. And when you hit the play button down here in the very bottom, hitting the play button causes these values to start changing. So we can see that my input voltage is fluctuating between 115 and 125. So that's going to be my simulated input voltage coming into this system. Okay, once you have started this and it's working okay, you don't want to stop it, you want to leave it running. Leave it up and running. Okay, and then we just want to close this window. Modbus PAL does have one slight little problem. If I were to leave this window open and then go back and try to create my, my Modbus slave and start playing around in there, as soon as you open up 2 or 3 windows, sub-windows, it crashes and hangs the application. So make sure I only work with one sub-window at a time. So I created my random generator, set my minimum and maximum values, and I went ahead and told it to start playing in the controls. Now I'm just going to close the window while it's still running. Okay? So we've now configured our automation. Now what we need to do is we need to go up to my Modbus slaves, and I need to add a Modbus slave. So I'm going to hit add. It's going to ask me what slaves I want to add. I'm going to go ahead and only add one slave. Okay, and my slave name is going to be voltage regulator. So I'm going to add one virtual simulated Modbus PLC, if you want to call it. Okay, this voltage regulator. So once you've added one, given it a name, you should see it pop up right here. And of course, you can get in and change the name if you want to at any point. Okay, so there's my voltage regulator. I want to go ahead and I want to edit this voltage regulator. So once again, click on that little eyeball. Okay, and that allows me to go in and edit the values inside of there. So this is my voltage regulator. These are all my different settings that we're going to set for our Modbus simulator. Okay, so inside of Modbus, remember how we talked about registers and coils? Okay, here's my holding registers. These are equivalent of my outputs. Okay, and then I have my coils, which are equivalent to my digital outputs. So these are analog outputs, digital outputs. Okay, we're going to first work with the very first one, my holding registers. Okay, on the holding registers, what I want to do for the holding registers is I want to go ahead and add some holding registers. By default, it's going to go ahead and add 1 to 65,000, which is fine. Go ahead and tell it OK. So it goes ahead and adds all these different registers for us. And I only want to configure the first 4. I don't want to do anything else with any of the other ones. And on these first 4, what I want to do is on the very first one, I want to have this as my input voltage. So I'm going to click on this very first value and tell it that I want to bind it. What this bind button does is the bind button basically takes this holding register and ties it to my input voltage automation that I created just a few minutes ago. Okay, so I'm going to say, yes, I want to bind it. That opens up this other little window. In this automation binding window, I want to go ahead and choose my input voltage automation that I created and tell it that it is a signed integer, 16-bit integer. Okay, so input voltage, signed integer 16. Okay, and then go ahead and tell it OK. That's all we need to do for this. And as you notice, I now have a value that's constantly changing, just like my input voltage. If that's not changing, make sure you check down here. Make sure the play button is playing. Notice mine's playing because I have a stop button here. So mine's already playing. So yes, I can see that my input voltage is already constantly changing. And then you can go ahead and give it a name. Okay, the name I'm going to give it is input voltage. So I have that name in there. When we give names of things in our control systems, we usually call these tags. So if you ever hear the name tag, this is a tag that I just named inside of this device. So this tag is input voltage. It is assigned to register value 1 or register address 1. Okay, now the next things I want to do. I want to go ahead and create the rest of my devices. So what I'm going to do is I'm going to go ahead and I'm going to do an input voltage. Then I'm going to create an output voltage because this is a voltage regulator. So I have an input and an output. And then I want to go ahead and set a low voltage alarm and a high voltage alarm. So if I ever see my output voltage going below 110 volts or going above 130 volts, it should trigger an alarm. Okay, now we don't really have an alarm here, but we're going to set this inside of the logic of our PLC that we're creating. Okay, so those are the 4 values I want to create. We already created the input voltage one that's bound to my input voltage. We want to go ahead and now just go ahead and create those last 3. So an output voltage, low voltage alarm, high voltage alarm. So I'm going to come in here, say this first one's going to be my output. 120 is what I want my output voltage to be. I want my alarm, low alarm, 110 is my low voltage alarm. And I want number 4 to be 130, which is my high voltage alarm. Okay, so that is the basic. This is a very, very basic controller that we're building right now. So input, output voltage, low voltage alarm, high voltage alarm. Okay, anybody have any questions? Having any problems with the tool so far? Okay. Give you guys just a second to get you finished configuring that window. Okay, the next one we want to do is we want to go ahead and we want to configure some coils for us. So, if we go over to the coils tab, there's 2 coils I want to configure. I want to go ahead and I want to configure an enable output. So it's going to be a switch on this voltage alarm to be able to say turn on output or turn off output, so that way we can remotely turn on and off this voltage regulator. Okay, so that's one of the first one is enable output. The second one we're going to do is a safety override. By default, we want to have that safety override turned off, so a 0 value, basically implying that if the voltage goes below or above those alarm areas, that this safety override will prevent that behavior. But if I turn this on, then that safety override will allow me to go ahead and produce voltages outside of those safe ranges. Okay, so I'm going to leave that off. Okay, so enable output, safety override are the two coils I'm going to create. So here I'm going to go to my coils. I'm going to go ahead and add coils and just go ahead and let them add all of them. That's fine. Okay, for my values, it's going to be a 1. And this is going to be my enable output. Go ahead and scoot it over so it looks a little nicer. And then that 0 value, I'm going to go ahead and say safety override. Okay, so safety override by default is turned off right now. Okay, so that is my basic voltage regulator. So this is just a very simple machine. This is going to now simulate this quote-unquote virtual PLC speaking Modbus and allow me to go ahead and read these values or change these values. Okay? So once I have this all configured, I'm going to go ahead and close this window. Notice they do have functions and timings and other things that we can actually do here. We're not going to be playing around with any of the functions or any of the features there. Okay, we're just playing with the coils and the registers. So we'll close that. And then back here on the main window, all we have left to do is go ahead and tell it to run. Now notice that this Modbus simulator can allow you to do serial communications, so you can actually simulate serial communications or TCP/IP communications. We're going to do the TCP/IP communications is what we're working on right now. Okay, so now this is running. Modbus simulator is up and running. I now have this virtual PLC running on my machine. It's listening on port 502. And by default, this listens on the loopback address. So 127.0.0.1 is its IP address. Okay? So this simulator is up and running. Now what we need to do is we need to have some tool to go through and communicate with it. We need to have a tool to be able to generate Modbus traffic. Now Modbus literally is so simple, you literally can open up a text editor, type the hexadecimal values that you want inside of that packet like we showed you in the previous screen, and you can pipe that into Netcat. And you literally can speak Modbus with Netcat. That's how easy the protocol is. But instead, we're going to use a dedicated Modbus client to be able to talk to the protocol. It makes it much easier to work with. Okay? The tool that we're going to use is called MBT-GET. So MBT-GET is a simple Perl program that allows us to communicate with Modbus. Right now, it's one of my favorite ones to use. I'm in the middle of actually writing a new tool written out of Python that actually will do all this functionality plus a whole bunch of other functionality. I wanted to extend this tool, but I didn't want to extend it in Perl, so I'm rewriting it in Python and extending it inside of Python, which I prefer to write in. Okay, so MBT-GET, it's inside the virtual machine. If you have the USB, I have the Perl script that was on that USB stick for you, so you can play with that. But if you just do a help page for MBT-GET, it goes through and shows you how you go through and work with this tool. So we have our command, we have all the different options, and then we go ahead and we have our serveur. Yeah, I didn't write the tool. So the running joke is it was in France, right? Where they wrote the tool. But here's our tool. So we have lots of different options. We have different types of commands that we can issue. So we have our read commands, read 1, 2, 3, and 4. Okay, and then we have our write 5 and 6. Notice the numbers correspond with the function numbers that we looked at in Modbus earlier this morning. Okay, so 1, 2, 3, 4, 5, and 6. Notice that this tool does not support a 15 or a 16, like what we saw in the PCAP file earlier this morning. Okay, so we're just going to do some basic reads and some basic writes. Other important values. We have a port number that we can specify. We have a Modbus address to specify that unit identifier. And we have some type of a value that we can go through and work with. So how many values do I want to read? So if I'm doing a read, I can say read 5 words of information from that device. Okay, so we want to go ahead and use MBT-GET. So I'm going to come back over here, open up a terminal, so just that little terminal at the very bottom. I'm going to open that up, and then for you, I'm going to go ahead and maximize my screen here so you can see a little better. Okay, and the nice thing about MBT Git has a whole bunch of defaults. In fact, it has enough defaults that, check this out, MBT Git. If you do it by itself, it'll actually read Modbus traffic from the simulator. It assumes port 502, it assumes unit ID 1, and it assumes the loopback address, which is what Modbus PAL is already listening on. So if you want to just check to see if Modbus PAL is actually working, that's the easiest way to do it. Just type MBT Git and it comes back up. Now realize, if you're in a control network or if you go through and you purchase your own PLC and you want to talk to it, you're going to have to give it more information to this. It won't automatically find it. In fact, what you're going to have to do is, what this is doing MBT Git is specifying that it wants address unit. Hold on, I forget my commands here. Let's see. Yeah, right values, the address, unit ID. It's assuming unit ID 1. It's assuming address 0, if I remember right. Nope, that was address. Oh, that was it. Yep, address 0 is what it's assuming. And then it is also assuming that we're doing an R3 value. Yep, that is the right assumption that it's making. And it's assuming that we're talking to port 502. And it's assuming that we're talking to 127.0.0.1. Let's go ahead and take that. Oops. 127.0.0.1. Okay, there we go. You guys, yep, you still see that. That's a good size. Okay, so that is my full Modbus command that's actually happening. It assumed all those defaults for me. But if you want to be able to use this tool in a normal network, plug your laptop into a normal network, and this is literally just change this to whatever you need it to be. Mostly what you'll be changing is the IP address. The rest of these values should be the same as almost any of your Modbus devices that you ever purchase or you're playing around with. They almost always will listen to use it to unit ID 1. They'll almost always have an address 0 that you can talk to, and reading R3 is just the register values that's there. Okay? So now what I want to do is I want to go ahead and I want to try to read all the different register values in this device. So I'm not changing the unit ID 1. I'm going to leave that one. I'm going to leave address 0. So it's saying I want to start reading at address 0. Okay? But what I'm going to add in here is an N3 or 4. I want to read 4 different words from this device. Okay, and if you want, you can clean this up if you don't like having the spaces in there, if you prefer having it that way. Oh, just kidding. It requires spaces. Sorry. I'll make sure I'll make my tool so it doesn't have the spaces for you. There we go. So what we did is we went ahead and just read those 4 values, the very first 4 register values. So we went ahead and saw the 16, we saw the 120, the 110, and the 130, which are all the values we have inside of my Modbus PAL. And if I keep on reading it and run that same command again and again, notice that address value number 1 keeps on changing. Here's a 116, here's a 115, here's a 115, I run it again, 115, run it again, 123. So that's that constantly changing input voltage. And all I'm doing is I'm using this client and said, hey, Modbus device out there, please tell me what your input voltage is. And it will go through and do it. Now, in a normal control network, what's going to happen is you're going to have a master server that is constantly pulling that device and making those readings. Most of the time, they'll make those every 2 seconds to be able to pull that information in. Could be greater or less than that, but 2 seconds is a very common pulling interval. Okay? So this allows us to go through and identify these different types of values. Now, a couple little things that you have to understand about Modbus. There's some gotchas here. Notice, what address am I reading in my command line? What address do I specify in the command line? I'm specifying address 0, right? I say read address 0. Okay? However, look at my output. What do they actually call it in the output? They call it output address 1. Let's look at my Modbus PAL. Inside of Modbus PAL, if I go into the configurations, notice address 1, oops, go to the right section. Address 1 is my input voltage. Okay? Inside of Modbus, this is a very common thing in Modbus, is that the protocol address that we're talking to almost always is 1 digit less than what it's actually listed at on most of the user-friendly screens. So all the operator screens start at 1. I guess it's too confusing to start at 0. I don't know why they started doing that. But the protocol itself actually starts at 0. So it's I would say 80% of the time that is the case. Every now and again you'll actually have an operator screen or a configuration screen that really does start at 0. So that's something you always have to watch for with Modbus, is to make sure that the commands really are the commands that you're thinking that you're sending. Okay? So that's the first thing to it. Here's the other thing to it. Inside of Modbus, I'm saying read address 0, and I want to read 4 words or 4 different address values. Okay? So I read 1, 2, 3, and 4. So I read all that information. Do you guys see the tags in there? Do you see the names? Do you see the word input voltage, or the input voltage there, or output voltage? Okay? Inside of the Modbus protocol does not support tags. Modbus protocol only supports addresses, which means if you're an attacker and you break into some type of a control network and you gain access to Modbus, yes, you can do anything you want with Modbus. There's no security. You can read anything, you can write anything, you can change anything. Send any control signal you want. But the problem is you don't know what to send. Because every single one of those control signals is tied to an address number. And unless you have this super decoder ring that says this address number is equal to this command, you're not going to know what to do. So what we do as attackers is what most of the attackers are going to do is when they get into the network, they might be able to speak Modbus, but most of them won't start speaking Modbus immediately. They will try to find their way to the HMI, which is a nice graphical interface where they can click on pretty buttons to control the process, or they will go through and they will try to find the engineering workstation, and on the engineering workstation, find the project files on the engineering workstation. Okay, because the project files on the engineering workstation has that configuration window that says address 1 is the input voltage, address 2 is the output voltage. And once you know what the tag's names are and what that function of the tag is and what address it works in, now I can go ahead and generate whatever Modbus traffic I want. But until I get to that point, an attacker is blind. Attacker doesn't know what he's doing inside of the network without having that tag information. Okay, so that's actually one of the saving graces for Modbus. You can do anything you want with Modbus, but you're blind unless you actually have the documentation for the specific system you're attacking. So, okay, so that's some issues or some items to note about these devices that's there. Okay, so that's reading the holding registers. We can go ahead and we can read the coils as well by simply changing this R3 over to an I think it's an R1. Yes, R1. Okay, so we can go ahead and say, go ahead and read our our coils. So R1 is coil, R3 is registers. So on the coils, I can go ahead and read my coil 1 and coil 2. And if you remember right, this was the enable output tag, and this one was the safety override tag. So this allowed me to go ahead and say, yes, turn the power on or turn the power off, or allow me to change the safety override, saying I can go ahead and have a totally different types of voltage setting that's there. Okay? So that's working with our system. Now, that's simple reading. Reading of these systems is very, very easy. We can keep on reading as we want, and you can go through and you can specify a whole bunch more than just 4. If this is a real-world device, you could go say, hey, let's go ahead and do 400 tags. Oh, 125 is the limit that this tool allows me to do. 125. Okay, so you can go through and read a whole bunch more values than what you really want. Part of the reason why I'm rewriting this tool to do something else is I want to be able to have a tool where I can go in and specify different types of enumeration values. Say I want to enumerate unit ID 1 to 5, and I want to enumerate addresses 1 to 65,000. I'll be able to put it in my tool and have my tool just automatically dump all that information for me. That's what I'm working on the new tool for. Okay, so let's change that holding value back to 4, change this back to a 3. Okay, so there are back to my registers. Now, on these registers, we can go ahead and we can change these different register values. We can go ahead and send write commands to them. Now, we don't really want to write to this one, right? That's our input voltage that's there. Instead, what's more interesting is change. What should we change on here? Should we change the output voltage? Put it to something higher than what it should be? See if we can change that? Okay, let's try doing that. Okay, so inside of this system, we can go ahead and we can say MBT get, so that same exact command, but instead of issuing a read command, instead we can go ahead and send a write command, a W6, which is writing a register value, to be able to go through and change a value. Now when we do that, we're not doing an N, because we're not writing multiple values. Instead, what we're going to do is W6, and we specify what value we want to write. So, what value should we write? Well, if we're changing my output voltage from 120, let's change that to something outside of these bounds, right? Let's go ahead and try changing it to 220, 240. So I'll say 240. Let's see if we can change the value to 240. Okay, said it wrote it okay. Let's go try reading it. So I'll up arrow twice, read my values again. Okay, coming inside of here, 220. Oh, hold on. Oh, because I changed I added address 0. That's what I did. So if I do this real fast, you can see, not fast enough. Oh well, let's just change that to the right value. So we want address 3. So once again, remember it's 1 off. So if I want to change this one, I have to do 4 minus 1. So I want to change that to 3. And then go ahead and do my read. So notice I did change that value now inside of it. So with Modbus, there's no security. It doesn't matter if there's some other server that's talking to this PLC controlling it. I can literally come with my laptop, go in and change any value I want, and that Modbus slave will say, okay, and change it. So, and unless that server is going through and constantly monitoring what's changed inside of it, has alarms on there, or there's some other security built in, there's nothing that we can do to stop people from doing this inside of once they're in the network. So, let's go look at Modbus PAL. Let's see if it changed things here. If I look in Modbus PAL, sure enough, notice it really did change it inside of my simulator. So this protocol is going through and modifying it and changing different values that's there. Okay? But by itself, that shouldn't work, right? Because we should have alarms going off right now. Because we have an alarm basically saying, oh, whoops, that wasn't the alarm. I didn't change the voltage output. What did I change? I changed the wrong tag. I changed the alarm value, right? Okay, what I wanted to change is the output value right here. So let's go change the output value. So we'll go change this one to a 1. And we'll read it. So now I have 240 there as well. So I've changed both of them. Okay, so now I've hopefully effectively killed off that alarm too. And then if I want to go change the coil, remember how we have the coil that says enable the safety override? Let's go ahead and enable safety override. I can come in here and instead of, oops, one more up. Instead of doing a W6, I can do a W5, which is writing to a coil. Okay, and when I write to the coil, I can go ahead and write a 1 to the coil, which basically turns on safety override, allowing me to override that safety mechanism to send whatever voltages I want. So I can go ahead and change that. Sure enough, that does write. Okay, and then I can go up and I can read that value now. Say I want to do an R1, and I want to read 2 of those values. Oops. Okay. Oh, and it did not change it. Once again, notice the number changed. I specified, right here, I specified 1, which should have been, no, write 1, address 1. That one actually should have changed it. Hold on. Write 5. I'm writing a 1 to 5, and I'm writing it to address 1. Okay, let's try, it shouldn't be 2. There, it was. Okay, weird. So that one's not 1 off for some reason. Okay, so I've been able to go ahead and change that safety override. So we now modified that one as well. So we can come back into Modbus PAL, look at this, look inside the coils. sure enough, I have been able to change all these values. Notice I did change that one on accident. So, yeah, that was weird how it was coming back strange like that. But we got it. So we got it all changed now. So we can go through with this tool, send any type of Modbus traffic we want, pull that information back, make any changes to it. So that's really the extent of Modbus. Very, very simple protocol. Now, if you ever want to play around with Modbus and dig into details with what's really going on behind the scenes, say that I'm sending this command where I am telling it to read a coil, and I want to read 2 coils starting at address 0. There is an option here that I can specify. That is a -H. Oops, not H. Where is it? Value hex, -hex, that's what it is. I can add the option -hex onto the command. No, that's not what I was meaning. It is right. D, that's what it is. -D. Dump. Okay, so if you want to see what the actual traffic looks like, you can go ahead and get a dump of that traffic. So here is my transmit traffic. Here's my response coming back with the actual values coming back. So if I look at this, notice that the very first 2 bytes is the transaction ID. So if I was come over here, step back up to right there. First 2 bytes are transaction IDs. So there's the first 2 bytes, transaction ID. Here is the version number of Modbus. Okay, so that protocol ID, all zeros, all zeros. Here is the size that we're actually sending. So we should have 6 bytes. We can count that. So there's 1 byte, 2 bytes, 3, 4, 5, and 6. So that's our length. And then the next one is going to be our unit ID. Notice unit ID 1. Okay, and then the actual command being sent is going to be a read 1. So that's going to be the function that I'm sending. And then the function's data is going to be the address and how many different types of how many different addresses to read. So I am reading from address 1, and I'm going to be reading 2 different coils from that address. And then when I get the reply back, notice the replies match, protocol's still there. It's saying that I have 4 bytes worth of data on unit 1, and I'm getting a read coil response message back. And since I asked for 2 coils, one of those coils is 01, one of them is 03 coming back. Okay, so that is my Modbus protocol. So very, very simple, straightforward protocol. You can go through and do it. Literally, you can take these, like I said, use netcat, paste that into netcat, and be able to play around with that. Okay? Now, how many of you guys were able to follow along with this inside of the virtual machine? Okay? Did anybody have any questions that was following along? Pretty straightforward? No problems. Okay. All right. So that is our simulator and playing around with it. Now we can go ahead and we can try to automate this and do something more with this tool. So instead of just going through and doing single reads like I was just doing, we can go ahead and we can try to throw this in different types of bash scripts to have it grab even more. So if you really wanted to, you could throw it in a bash script, give it some type of a range, so for I in some type of a range, then go ahead and do a read and have it read as many values as you want. So it stopped me from reading more than 125 values. If I want to read 1,000 values, stick it into a little script to go through and to change those values. Okay, so if I come in here, I'm just going to cheat and paste this so I don't have to type the whole thing. Let's hope it actually comes across cleanly over here. Yes, it does. So there's all of my coils just going through and reading multiple different coils inside of this system, reading 1,000 of them. Okay, so this is a great way to go through and do the enumeration, and this is what I'm trying to add default in the tool so you don't have to script anything. So you can go ahead and you can change those values for enumerating them, or you can go ahead and if instead you want to try to monitor the values in the coils, so kind of similar to how the Modbus servers do, they're constantly polling to see what's there, you can write your own little script to go through and start monitoring which register values are changing. So if I was to come in here, oops, let me change the number here. So I'm doing MBT get. My mic doesn't like me hanging over that far. let's look at address 0, because that's the one that's constantly changing. Okay, so if I want to just constantly pull that device, you can go through and see what time that is and what that value is actually changing to over time. So if you're an attacker and you don't have access to the tools, this is one thing that attackers will commonly do, is they'll pull your own devices, see what you're actually changing. If they don't have access to the traffic, they'll just keep on asking and try and see what's going on inside the device. So this is one of the things you want to try to detect from a defensive perspective, is trying to detect when people are generating new traffic inside of that network. Okay. So that is doing basic enumeration for the tool. Now, besides doing enumeration, we can go ahead and we can do some fuzzing of Modbus as well. So when we enumerating Modbus just means that we're just reading different types of values, learning about the system, maybe going through and changing it, trying to change some values in there. But we can also go through and try fuzzing the protocol to try to identify if we can break the protocol or break that implementation of the protocol and find some type of a vulnerability. Now, this is beneficial. If we can find a vulnerability like a buffer overflow, literally using some simple protocol like Modbus, we might be able to find or write some type of a Metasploit payload and be able to gain a interpreter instance on the master server themselves. Okay, so a lot of times inside of our control networks, they'll have the master server, and that master server will be talking to some type of a PLC speaking Modbus or a control system protocol, and they automatically think, well, that's just a control system protocol. But in reality, that's all that, it's a TCP/IP connection that we can generate and do anything we want with if we take over the process on one of the ends. So by finding a vulnerability and uploading some type of an interpreter payload through Metasploit, we can gain control over that upper end point and be able to have a presence on that server, even in something as simple as Modbus. Okay, so that's probably one of our biggest concerns when we talk about security, is somebody not just getting their hands on a PLC, but somebody getting their hands on a PLC, replacing it with their own tool, and then trying to attack the master servers from that network point. Okay, so when we're doing fuzzing, we can go through and we can try to put in different, or try to speak that Modbus protocol, but try to randomly change, either purely random or more strategically, trying to cause different types of crashes or freezes inside of the instance. So when we do fuzzing, what we're really looking for is a way to freeze the process or stop the process or watch that process to go through and restart, or have some other type of strange errant behavior inside of that process. Okay? Now when we're doing this, there's a couple ways we can do fuzzing. We can go through and we can do mutation-based fuzzing, which means that I capture some Modbus traffic, I feed that into a mutation fuzzer, and it uses that PCAP to generate variations or mutations of that traffic to try to attack the endpoints to it. And we can attack the PLCs in the requests, or we can go ahead and we can set up the servers to keep on pulling something, and I can set up my fuzzer as a virtual PLC and have it reply to that master's request so I can actually fuzz the master. Now, when people are doing fuzzing, guess which one most people are fuzzing? Most people are fuzzing the PLCs. Most people are actually generating the fuzz messages, sending the request back out. A lot of people that are doing fuzz testing, they're not fuzz testing the servers because you have to come back in on a reply. So you have to find a server, you have to set up the server to start doing polling, and then you have to pull as fast as you can so that way I can go ahead and keep on trying to attack that master process coming back in. In fact, it's been such a problem that we've found over the last couple of years, our ICS protocols, there's been a number of different vulnerabilities that have affected the clients, but not a lot of vulnerabilities were ever reported that affected the servers on the response messages until a group of individuals wrote a tool called Aegis, which we'll talk about in just a minute, that went through and could fuzz either end of that conversation. And after their tool was out, they actually started doing the server side, and almost every single server implementation they tested for the DMP3 protocol, so kind of the replacement protocol for Modbus, a more advanced one. They found almost every single server instance actually had serious high-level vulnerabilities built into it. And so they ended up having like 30 different vulnerability bulletins come out for 30 different products from ICS CERT, which is one of the big clearinghouses for all of our vulnerabilities for the ICS community. Okay? So mutation fuzzers work really well because we just simply grab a PCAP file and it just changes it. The fuzzer doesn't need to necessarily know a lot about the protocol. And so mutation fuzzing is kind of an easy way to do things. Generation-based fuzzers often can be a little bit more targeted, but the problem is in order to use a generation fuzzer, you have to train that fuzzer how to speak the protocol. Okay, so most of the best fuzzers out there will generally have a combination of both capabilities. They can do mutation or they can do generation. Generations often are the best because we can go through and do generation fuzzing and say, hey, focus on this section, and this section, and focus on these ranges that are outside of the spec that we aren't really defined on how they're supposed to work. And then they can do a better job at, hopefully have a higher odds of finding vulnerabilities inside of the system. Now, there's lots of different tools that are out there. We end up having 2 different fuzzers inside of Samurai STFU for our purposes. We have one fuzzer that's called Peach Fuzzer. Have anybody used Peach Fuzzer before? Okay, Peach Fuzzer, great fuzzer. So I used to use Sully a lot. Sully used to be one of my favorite fuzzers that was out there. It was written in Python. But Sully just really doesn't have a lot of support. It hasn't been maintained for years and has some weird fluky things to it. Peach Fuzzer is one that has been maintained, and there's a professional company behind it, so you can actually buy commercial support or just use the free version of it. The first 2 versions of Peach Fuzzer were written in Python. When they went to version 3 of Peach Fuzzer, they went ahead and they rewrote the entire stack in .NET, but they made sure that everything they did was compatible with Mono, so you can actually run it in Linux as well as Windows. So it works really, really well that way. Okay, Aegis is another fuzzer that's out there. Aegis is a fuzzer that's written in C. It's one specific for ICS protocols. It is a proprietary, closed source protocol that's out there, but we happen to have a version of it for the first release of it was released here inside of our distribution. So we do have the initial release of Aegis, which they did release to the public. All future versions of Aegis after that were closed source. So the current version out there right now only does, so the one I have right now only does DNP3 protocol. The commercial version, if you go out and buy a copy, does DNP3 and Modbus. So we don't have the Modbus instance. So we're not going to be playing around with Aegis. But with Peach Fuzzer, so Michael Eddington and Deja Vu Security. Deja Vu Security is the company that owns Peach Fuzzer, open source. Michael Eddington is the main developer, and he often will come to some events like Black Hat and teach how to use Peach Fuzzer. He does that in the Vegas show. But it's one that's written in C++ or C#, .NET, and Mono. A great tool, cross-platform, works on all the major operating systems. It does mutational fuzzing and generation-based fuzzing. It has very, very strong capabilities to model the states, which is necessary for some of our more complex protocols. And it's nice because it has pluggable I/O adapters, which means that you can use Peach Fuzzer to go through and fuzz file protocols. Like, so you have an application that opens up a file like a Word document. Okay, you can use Peach Fuzzing to do that. You can use Peach Fuzzing for network communications. You can even use Peach Fuzzing for hardware. Okay, so I taught the last 2 days. Yesterday in the Assessing and Exploiting Control Systems class, our class went ahead and we were working with embedded protocols like SPI and I2C. You can actually fuzz I2C and SPI with Peach Fuzzer. Okay, very, very flexible fuzzing tool that's out there. Now, in order to go through and use Peach Fuzzer to fuzz the Modbus protocol, you have to build a state table. Basically, teach it how to speak Modbus. Okay, so I've done that. This is a very basic implementation of Modbus. This is how we would configure it. So I go through and say, inside of Peach Fuzzer, create an XML document for Modbus saying, hey, my data model is Modbus request. My request has a transaction ID that's 16 bits. It's a hexadecimal value. The default value, we'll call it 1. It has a protocol ID that's always going to be 0. And then it has a length identifier that is a 16-bit length, and it has a whole bunch of stuff inside of it. Okay, and then I can come down here and say, okay, my block stuff ends up having a unit identifier, a function code, an address size, and a number of bytes that we're going to read. So this basically tells and teaches Peach Fuzzer how to create a Modbus request. So same, just the state table, how to speak that value. Okay. Then the next thing we want to do is we have to teach it how to do a response as well, because if we want to fuzz both directions, I have to be able to do a request and a response, so that way I know how to finish the conversation. Okay, so I can go ahead and create a model for Modbus response, and I say my Modbus response references Modbus request, because most of the packet or most of the sections are the same, so I can just say, hey, reference this other one, and I'll tell you what's different. So start from over here, and I'll tell you what's different. And what's different? Well, it's the stuff that's different. So I'm going to change the stuff saying unit ID is going to be the hex value, my function code, and then the data size coming back, and then the size of whatever information is coming back based on how many values I've read. Okay, so that's basically building my models for it, for a Peach Fuzzer. And then inside of Peach Fuzzer, I have to go through and I have to create a state model, basically telling it how the request and responses associate to each other. Modbus is easy. I have one request, I have one response. Very, very straightforward. There's other protocols that are much more complex than this. But this one's easy. So my state has an output, which I use the Modbus request for, and then I have an input, that's the Modbus response coming back. So it's a very, very simple state model. If you start modeling other protocols, it gets much more complex than that. Okay? And then for my agent, I can go through inside of, I want to have some type of an agent that's monitoring what's going on to be able to detect when there's been some type of a crash. I can go through and say monitor class is going to be PCAP. So the way I'm going to monitor this fuzzing instance is with a PCAP file, have it capture all that traffic. Okay? The device that I'm capturing on is just my loopback address because I'm doing this to my fuzzer locally, my Modbus PAL simulator. I'm going to be working on port 502. The host that I'm talking to is my loopback address. So this is configured to work with Modbus PAL fuzzer that I've already created. Okay? And that's pretty much it for setting up my Modbus fuzzing agent. The very last thing we have to do is we have to create a publisher that basically tells it how to start the process. So we say, hey, we have our publisher. It's going to have a control iteration, meaning every 10 requests, it's going to repeat a golden request or a predictable request to make sure that we haven't broken something. So it makes 10 fuzz attempts, and then it goes ahead and sends out a golden request to make sure that the server's still responding appropriately. And then it sends out 10 more fuzz requests, and then it checks to see if the server's still talking appropriately. Okay? Then it goes through, it builds a TCP client to go through and send out and communicate to that IP address and port number, and goes ahead and logs everything at this location for me with the logger. Okay, so that's configuring Peach Fuzzer. A little bit long-worded, but it's pretty straightforward once you do it a couple times with Peach. Okay, so what we're going to do is I've already created one inside of the virtual machine for Modbus. So the one we walked through is already inside of the virtual machine. So all we have to do is go to the virtual machine, change our terminal over to word list Peach Pits, and inside of there we just go ahead and run sudo peach modbus-tcp-xml, which is the configuration file, -1 debug. And what that's going to do is it's going to send out one single request, which is what that one is, and it's going to show me a debug message back, show me details of what's going on inside of that range. And if the debug message works properly, which hopefully it does, I haven't tested, I haven't made sure I haven't broken Peach in the last update. Then we'll go ahead and we'll say sudo peach modbus range 1 to 100. Say basically send out 100 different fuzz attempts. Okay, so let's go ahead and try this. Come in here, I'm going to clear, I'm going to CD over to word lists, Peach Pits, and inside of there I should see my file. So there's my Modbus TCP that I created. I'm going to go ahead and run sudo peach modbus XML, tell it that I want to do a test of 1 and --debug. Okay, so it starts up Peach, it parses the file, it parses it okay, looks everything good. Validation not supported in the model runtime. Okay, so that seems to everything look good there. Let's go ahead and change this now and go ahead and do, let's see, range 0 to 100. Range 0, 100. Starts up Peach, goes ahead and starts doing the testing string, and then it starts going through and sending the fuzzing attempts that are out there. So this is the 4th message it's sent, then the 4th, the 5th message, the 6th message, 12th message. If I scroll back up, remember how I said to do a control iteration every 10? The control iteration's right here. So I have 9, C10 is my control iteration. That's that golden packet to make sure everything's working properly. And then it sends out my fuzz attempt number 10. Okay, so this is the golden packet, make sure it works. If that failed, it wouldn't have went ahead and sent the next message. So that passed. We scroll down a little more, 12, 13. Okay, control iteration 2. That worked because it kept on going. If it ever gets to a control iteration that fails, it'll stop the fuzzer. There's control iteration 3, so that seemed to work okay. Oh, it's doing number 4 now. When it's doing it, notice what it's doing. So here's the fuzzing. It's going through and telling you exactly which values it's changing and which mutators they're working with and how they're mutating it. So we can tell exactly what's changing each one. So some of the fuzz requests only change a couple values. Other ones change a lot of values. So it based on the random generator to figure that out. There's control iteration 40, or number 4. Control iteration 5. Control iteration 6. Notice how some of these are taking longer than other ones. Most of the reason why is because Modbus PAL is freaking out at some of this traffic and not replying to us very quickly. Control iteration 7 passed. Okay, and so this is slow. This is not Peach that's slow. This literally is Modbus PAL that's replying slowly to it. And I'll show you, if we have time, maybe I'll show you Aegis real fast. Actually, we're not going to have time because we're right at the very end. So we're about 6 minutes left. Anyway, so that's going through and fuzzing. And usually if you keep on running this, it looks like we're actually going to make it through all 100 iterations just fine. But if you're doing this on your own machines, did anybody have it stop on one of the control iterations? About 50% of the times, it'll stop at one of the control iterations before 100. Okay, and then the other 50% of the time, it actually makes it. So it all depends on the random traffic that you're actually sending to see if it worked or not. And mine actually successfully passed all of them without any issues. Okay? So that is fuzzing Modbus. So we can do enumeration on Modbus. We can do fuzzing on Modbus with a tool like Peach. Okay? So that's pretty much it for our workshop. We have about 5 minutes left before we get to our lunch break. So let's go ahead and open that up for questions. Does anybody have any questions about Modbus or just the material in general that we've been discussing this morning? So the question is because Modbus is so simple with no security, what can we do to try to improve the security of Modbus? Well, the biggest thing we need to do is we have the interim. What can we do right now? And then what can we do about the future? So right now, the best thing we can do if we have something like Modbus is to, number one, keep the attackers away from Modbus. So we want to go through and make sure that if you're an organization that's control networks, make sure you have good internet perimeter defenses, because that's where most of the attackers are coming from. Make sure you have good perimeter defenses between the corporate networks and the control networks. And inside of the control network, you should not have any device inside of the control network. No workstation should be able to get to the internet. You shouldn't be surfing. You shouldn't be able to even get to email inside of the control network. What we recommend is control engineers, if they need to get to corporate email, they have a corporate machine to do that. And to work in the control network, they have a control machine to do that. And so we have a very, very tight perimeter between control and corporate. And then inside of the control network, you want to have multiple different perimeters there as well. So defense in depth, keeping the attackers away. So that's the first thing we do. If we ever have Modbus that needs to pass some type of a link that has a higher chance of being attacked, maybe some type of remote connectivity, make sure you throw it through a VPN tunnel. Okay, which the VPN tunnel will give you a way to be able to do authentication and encryption to protect that traffic there. We also can go down and buy special application-aware firewalls and mount them right next to our PLCs. There's a number of different manufacturers that you can buy that mounts right next to the PLCs, mounts on the same DIN rails and uses the same 24-volt power to it, that you can run the network cables to that first and then have that connect to the PLC. And you can create firewall rules saying, only allow this IP address from the master server to talk to it. Don't allow anybody else to do it. In fact, you can also, on the application-aware one, say that the master server from this IP address is only allowed to send write messages to these 5 addresses. So it's an application-aware firewall rule set. So that's what we can do right now. What can we do about the future? We need to start getting better protocols that has security built into them. And IEC, one of the international, probably the most common or the biggest international standards body that works with our ICS protocols, they currently have a working group set up right now to go through and create security, authentication, and package signing and optional encryption on a lot of the protocols that are out there right now. So there's some protocols that have it, like DNP3 as a replacement for Modbus, and there's a secure version of DNP3. That's an option to use. There's also 61850 MMS, which is an option that we can use as well. Mhm. Yes. So the scanning objects that will go through and do it, most of the policies, if you look at something like Nmap, there's a Modbus NSE script for Nmap, and all it does is enumeration. So if it finds something on port 502, it goes through and it tries to pull down identifiable information for unit ID 1, maybe more, depending on if you tweak that NSE script. If you look at things like Nessus and Qualys, Nessus and Qualys have some audit capabilities for some ICS protocols that are out there. If it's Modbus specific, it's probably enumeration type information. If it is something that is product specific, so talking about a specific product from a vendor, what that will usually do is it will log into the Windows or the Linux server via RDP or an SSH shell. It'll go through the configuration files and look for different settings inside of their secure settings. There's a company out there that it's called Digital Bond. They created a free project called Bandolier, which has a lot of different audit policies that you can feed inside of Nessus. And that's been the source for a lot of what the scanning vendors have done for vulnerability scanning tools. Yeah, but port scanning and vulnerability scanning, field devices like PLCs, you have to be very careful. It's very easy. It's not uncommon for you to actually crash them because the PLCs don't have good capabilities inside of their tools. Okay. Any other questions? All right. Thank you very much, and I'll be around here if you have any other questions. Feel free to come up afterwards, and I'll be more than happy to talk to you. Thanks for joining us, and I hope you guys enjoyed the rest of the conference.